So we conclude this section with an example of an application that you encounter sometimes when you look for ways of making use of the recently learned theorem, the squeeze theorem. So again, we're still on 2.6. It says sometimes we want to compute limits of this type. Suppose we're asked to compute the limit of x squared times cosine of 1 over x as x approaches 0. So this is a limit where the known limits that we just computed, so namely the sine x over x or 1 minus cosine of x over x, are not useful, and still a trigonometric limit, but those limits are actually play no role at all, and this cannot be simplified algebraically, so we need to resort to something else. In this case is the squeeze theorem. And the idea, and in all the applications you'll see, I mean, I bet you, I mean, no one will actually do anything different from what we're going to do, what we're about to do now. So you have a function that its only property, I mean, it is bounded. Probably the function is not converting to anything to the at the point. In this case, x equals 0, and that function is cosine of 1 over x. This is one of the earliest examples of functions that would not have a limit as we approach the origin, because it oscillates a lot. So it goes back and forth between between -1 and 1, and takes on all the values in between infinitely often as you approach the origin, so it's not converging anywhere, but it's bounded. And then this will allow us to use the squeeze theorem to obtain the limit is in fact 0 for this particular example. So how do we compute? So we appeal to the squeeze theorem one more time, and remember that the squeeze theorem asks us to find two functions, L of x and U of x, so a lower bound and an upper bound. So here what we're going to use, L of x is going to be the function minus x squared, and while the function U of x is going to be simply x squared. So how do we use this? And in all the applications you will see, I mean, I guarantee this is all you'll need to do. You need to identify one of the functions in this kind of product that is going to be bounded. In this case is cosine of 1 over x. True, cosine of 1 over x doesn't approach anything as x approaches 0, but it's bounded. Cosine, no matter of any number, cosine of any number is trapped between 1 and -1. So we have this inequality here. So cosine of 1 over x can never be, I mean, no matter how small x is, it doesn't matter actually the value of x, as long as it's not 0, so you can actually compute the cosine of 1 over x. But the cosine of 1 over x can never be smaller than -1 or bigger than 1. And so how do we obtain, and this is the other point in this kind of problem, so how do we obtain the expression x squared here? Well, we should multiply cosine of 1 over x by x squared. So we'll multiply by x squared on every side here of the inequality, and since x squared is positive, we preserve the inequality, so we get minus x squared is less than or equal to x squared times cosine of 1 over x, and is less than or equal to x squared. And this is why I said that we recognize here that this is L of x, and this that we have on the right hand side is U of x. But we know that when we let x go to 0, both L of x and U of x go to 0. So this goes to 0, and this goes to 0 as well, as x approaches 0, and this x approaches 0. So the conclusion here, using the squeeze theorem, is that x squared cosine of 1 over x goes to 0 as x goes to 0. Okay, so this is the last kind of problems that you will be required to solve using the squeeze theorem. And it's always the same thing, so there's a quantity, so it's usually a product. And the structure is the same, so a product, one of the factors is approaching 0, and the other one is bounded. Therefore, you proceed like you do the exact same thing here. Of course, the cosine is bounded between -1 and 1, but for other examples, you may have different bounds. But then we multiply things on both sides, and we get the desired L and U, and we get our function trapped between the two L's, the two functions L and U, and we let x go to 0, and that's how this works. Okay, so this is for now. This is good for now. Then we'll move on to section 2.7. This is limits at infinity, and that's for the next video.